What if I told you that the most common planets in the universe don't exist in our solar system? And what if these mysterious worlds could be the key to finding alien life? Today, we're diving into the fascinating realm of Sub-Neptunes. Planets so strange, they're rewriting everything we thought we knew about the cosmos. But before we begin this incredible journey, let me ask you this. Have you ever wondered why we haven't found planets like these in our own solar system, yet they dominate the galaxy? The answer might shock you and completely change how you think about our place in the universe. Welcome back to BrightBoundX, where we explore the brightest frontiers of science and space exploration. I'm your host, and today, we're uncovering one of the most groundbreaking discoveries in exoplanet research that's sending shockwaves through the entire scientific community. Scientists have just revealed how these enigmatic worlds called Sub-Neptunes might be our best indirect pathway to discovering life beyond Earth. This isn't just another space discovery. This could fundamentally change how we search for alien civilizations and potentially answer the age-old question: are we alone in the universe? The research I'm about to share with you involves some of the most advanced space technology ever created, mind-bending physics that pushes the boundaries of our understanding, and implications that could reshape humanity's cosmic perspective forever. So buckle up, because we're about to embark on a journey to worlds so alien they make science fiction look mundane. Picture this incredible scenario: the James Webb Space Telescope, humanity's most powerful eye in space, worth over $10 billion, and representing decades of international collaboration, has just detected water vapor on mysterious planets that represent the most abundant type of world in our galaxy. We're not talking about a few isolated cases. These planets are literally everywhere we look in the cosmos, yet they're completely absent from our own cosmic neighborhood. It's like discovering that the most popular car model in the world doesn't exist in your entire country, or finding out that the most common type of tree on Earth somehow never evolved in your local forest. The statistical improbability of this situation is staggering and suggests something profound about the uniqueness of our solar system's formation history. Leading researchers Professor Natalie Batalha and Professor Jonathan Fortney from UC Santa Cruz have published groundbreaking findings in the Astrophysical Journal that are sending shockwaves through the scientific community worldwide. Their research reveals that Sub-Neptunes planets similar to Neptune but significantly smaller, typically ranging from 2 to 4 times Earth's radius, are offering us unprecedented clues about where life might exist in the universe. These aren't just academic curiosities that exist in theoretical papers. They're potential roadmaps to the greatest discovery in human history. Every sub-Neptune we study brings us closer to understanding the fundamental processes that govern planetary formation, atmospheric evolution, and the distribution of water throughout the galaxy, all critical factors in the emergence and sustainability of life as we know it. Here's where the mystery becomes absolutely mind-blowing and statistically almost impossible to explain through coincidence alone. Sub-Neptunes are the most common type of exoplanet we've discovered, making up roughly 30 to 50% of all known exoplanet across thousands of different star systems we've observed. That's potentially hundreds of billions of these worlds throughout our galaxy alone, yet they're completely absent from our own solar system. Think about that extraordinary fact for a moment. The most abundant planetary type in the universe, more common than Earth-like rocky planets, more common than gas giants like Jupiter, more common than ice giants like Neptune, simply doesn't exist anywhere near us. It's as if we're living in a cosmic anomaly, surrounded by planetary types that are rare throughout the galaxy, while the common ones exist everywhere else but here. This statistical anomaly raises profound questions about solar system formation, planetary migration, and the processes that led to the unique architecture of our cosmic home. Did something unusual happen during our solar system's formation 4.5 billion years ago that prevented sub-Neptunes from forming or surviving? Or did they form and then migrate away? or get ejected from our system through gravitational interactions, we're only beginning to understand. But what makes these absent neighbors so special that their study could revolutionize our understanding of life in the universe? Initially, scientists tried to understand these planets using computational models originally developed for studying icy moons like Europa and Enceladus. However, the new research reveals that sub-Neptunes are entirely different beasts altogether, operating according to physical principles that create conditions unlike anything found in our solar system. Unlike the familiar icy moons with their frozen crusts hiding liquid oceans beneath relatively thin ice shells, sub-Neptunes possess something far more exotic and fundamentally alien in their structure and composition. These worlds develop thick water vapor atmospheres that can extend thousands of kilometers above their surfaces, creating atmospheric pressures and density gradients that dwarf anything found on planets in our solar system. Deep within these atmospheres and the planetary interiors below, we encounter layers of what scientists call matter that exists water, a bizarre and almost magical state of water is subjected to temperatures above 374 degrees Celsius and pressures more than 221 times Earth's atmospheric pressure. In this state, water exhibits properties that are simultaneously liquid-like and gas-like, with no distinct phase boundary between the two states. But the physics gets even more incredible and seemingly science fiction like when we delve deeper into these worlds. Under the extreme conditions that exist in the cores of sub-Neptunes, with pressures reaching millions of times Earth's atmospheric pressure and temperatures soaring to thousands of degrees Celsius, water can undergo a transformation into what scientists call superionic ice, a state of matter so exotic it was only theoretical until recent laboratory breakthroughs confirmed its existence. In superionic ice, the water molecules reorganize themselves in a crystalline structure where the oxygen atoms remain locked in place like a solid, while the hydrogen ions become mobile and can move freely through this oxygen lattice structure like electrons in a metal conductor. Imagine ice that conducts electricity like copper wire while maintaining some structural properties of solid water. That's the kind of alien physics we're dealing with in the cores of these distant worlds. This superionic ice could make up entire layers within these planets, potentially comprising thousands of kilometers of planetary interior, creating internal dynamics, heat flow patterns, and magnetic field generation mechanisms that we're only beginning to model and understand. These aren't just different planets. They're operating according to physical principles that push the absolute boundaries of our understanding of matter and energy under extreme conditions. The UC Santa Cruz team has developed revolutionary new computational models that represent a quantum leap forward in our ability to understand these exotic worlds. These models account for water's behavior under extreme conditions by incorporating experimental data from cutting-edge laboratory experiments that recreate the intense pressures and temperatures found deep within sub-Neptunes using diamond anvil cells, laser heating, and other advanced techniques. This isn't just academic curiosity or theoretical physics divorced from observational reality. It's detective work on a cosmic scale, using cutting-edge physics, chemistry, material science, and computational modeling to decode the secrets of distant worlds that we can observe, but may never visit. The interdisciplinary nature of this research represents a new paradigm in planetary science, bringing together expertise from multiple fields to tackle questions that no single discipline could address alone. By accurately modeling how water distributes, behaves, and transforms across these common worlds under varying conditions of temperature, pressure, and time, scientists can trace how water and other volatiles move during planetary system formation across billions of years of cosmic evolution. They're essentially creating detailed geological and atmospheric histories of planets that formed when our own solar system was young, providing insights into planetary formation processes that occurred throughout the galaxy's 13 billion-year history. The computational challenges involved in this modeling are staggering, requiring supercomputer simulations that track the behavior of matter under conditions more extreme than those found in the cores of stars. Each simulation represents months of computational time on some of the world's most powerful computers, generating terabytes of data that must be analyzed to understand how these worlds form, evolve, and potentially influence the development of life in their stellar neighborhoods. This is essentially following the breadcrumbs of life itself across cosmic history, because water and its behavior under various conditions throughout a planet's evolution is one of the primary factors determining whether that world might ever develop or maintain the complex chemistry that underlies biological processes as we understand them. Co-author Artem Agachin explains the profound implications of this research with remarkable clarity and vision. When we understand how the most commonly observed planets in the universe form, we can shift our focus to less common exoplanet that might actually harbor life. This seemingly simple statement represents a fundamental paradigm shift in our approach to astrobiology, the search for extraterrestrial intelligence, and our understanding of planetary formation on galactic scales. Think of Sub-Neptunes as cosmic stepping stones, universal laboratories, or galactic textbooks that teach us about the fundamental processes governing planetary formation, atmospheric evolution, and the distribution of water and organic compounds throughout the galaxy. By understanding these abundant worlds that exist in virtually every planetary system we've studied, we're building a comprehensive theoretical framework and observational foundation that guides us toward identifying the rarer, potentially habitable worlds where life might actually exist, evolve, and thrive over geological timescales. The implications extend far beyond individual planets or even individual stellar systems. We're learning about the fundamental astrophysical processes that govern how entire galaxies form stellar and planetary populations, how water and other life-essential elements distribute during galactic chemical evolution, and how different environmental conditions throughout cosmic history might have supported or hindered the emergence of life on scales we're only beginning to comprehend. This research is helping us understand why certain types of planets form in some stellar systems, but not others, how planetary migration and gravitational interactions shape the final architecture of mature planetary systems, and how the timing of planet formation relative to stellar evolution affects the long-term habitability potential of worlds throughout the galaxy. The James Webb Space Telescope's confirmation of water vapor on these worlds represents a watershed moment in the history of astronomy and our technological capability to study the universe in unprecedented detail. We're not just observing distant planets as faint points of light anymore. We're analyzing their atmospheric composition with spectroscopic precision, understanding their internal structure through gravitational modeling, and even detecting weather patterns, seasonal changes, and atmospheric dynamics on worlds hundreds or thousands of light years away. Each spectroscopic observation reveals the detailed chemical fingerprints of these distant atmospheres, allowing us to build three-dimensional models of worlds we may never visit, but can understand in remarkable detail. The telescope's advanced instruments can detect not just the presence of water vapor, but its vertical distribution throughout the atmosphere, temperature and pressure variations at different altitudes, and even seasonal changes in atmospheric composition as these planets orbit their host stars. This technology represents one of humanity's greatest achievements in engineering, optics, and space exploration, essentially allowing us to perform sophisticated chemistry experiments on planets orbiting other stars. We're analyzing alien atmospheres with greater precision than we could study Earth's atmosphere just a few decades ago, detecting molecular species, isotope ratios, and atmospheric processes that reveal the formation, history, and evolution of these distant worlds. The James Webb Space Telescope is essentially a time machine that shows us these worlds as they existed when the light left them years, decades, or even centuries ago, providing snapshots of planetary evolution across different stages of stellar system development. Each observation adds another piece to the cosmic puzzle of how planets form, evolve, and potentially develop conditions suitable for life. What does this groundbreaking research mean for our search for extraterrestrial life and potentially intelligent civilizations beyond Earth? Sub-Neptunes are teaching us that the universe is far more diverse, complex, and creative in generating planetary environments than we previously imagined, with formation processes creating worlds that operate according to physical principles we're only beginning to understand and appreciate. By studying these water-rich worlds and their exotic atmospheric and interior conditions, we're learning how planetary systems evolve over billions of years and where the optimal conditions for life might arise and persist throughout cosmic history. The research suggests that our traditional approach to finding life searching primarily for Earth twin planets with similar sizes, compositions, and orbital characteristics needs to be dramatically expanded and made more sophisticated. Instead of limiting our search to exact replicas of our world, we need to develop a comprehensive understanding of the full spectrum of planetary types, their formation and evolution processes, and how they might influence the potential for biology to emerge, evolve, and survive in environments that could be radically different from Earth's relatively calm and stable conditions throughout most of its history. Sub-Neptunes are expanding our definition of habitability and forcing astrobiologists to consider that life might arise and thrive in environments far different from Earth's surface conditions. While these worlds themselves might not be directly habitable in the traditional sense, they could influence the habitability of other planets in their systems through gravitational interactions, or they might even harbor life in atmospheric zones where temperature and pressure conditions allow for liquid water chemistry. Water is universally recognized as the essential solvent for life, as we understand it, and sub-Neptunes are essentially serving as cosmic laboratories for understanding how water behaves, transforms, and distributes under extreme conditions that don't exist anywhere in our solar system, but could be common throughout the galaxy and universe. The supercritical water and superionic ice found on these worlds represent physical states that we can barely recreate and study in Earth-based laboratory experiments, yet they could represent the dominant forms of water throughout the cosmos. Understanding these exotic water phases and their chemical properties helps us predict where liquid water might persist and remain chemically active in planetary systems under conditions we previously thought were completely incompatible with water-based chemistry. This expanding understanding of water chemistry under extreme conditions is like learning entirely new dialects of the universal language of chemistry, languages that could help us communicate with the universe about where life might flourish in forms and environments we haven't yet imagined or seriously considered in our search strategies. The research is forcing astrobiologists, planetary scientists, and researchers involved in the search for extraterrestrial intelligence to expand their thinking about the environmental conditions that might support life, moving beyond Earth-centric assumptions toward a more universal and comprehensive understanding of the physics and chemistry that could underlie biological processes throughout the cosmos. The fact that we can detect, analyze, and model water vapor on planets hundreds of light years away, determine their detailed atmospheric composition, and understand their internal structure and dynamics represents one of the greatest technological achievements in human history, and our species' growing capability to study the knowledge and techniques being developed through sub-Neptune research are already influencing the design of future space missions, next-generation ground-based observatories, and advanced space-based instruments that will study exoplanetary atmospheres and interiors in even greater detail over the coming decades. The upcoming extremely large telescopes, with mirrors 30 to 40 meters in diameter, and advanced space-based observatories will be equipped with revolutionary technology specifically designed to study atmospheric composition, weather patterns, seasonal changes, and even potential biosignatures on these distant worlds with unprecedented precision and sensitivity. We're rapidly approaching an era where we'll be able to create detailed weather maps of exoplanetary atmospheres, track storm systems and seasonal changes on worlds in distant solar systems, detect atmospheric chemistry that might indicate geological or biological activity, and potentially identify atmospheric signatures that could represent technological civilizations modifying their planetary environments. The technological capabilities being developed today through Sub-Neptune research will transform our understanding of planetary science, atmospheric physics, and astrobiology within the next decade, opening entirely new avenues for studying the universe and our place within it. This groundbreaking research demonstrates how modern astronomy and planetary science have evolved into deeply interdisciplinary endeavors, requiring seamless collaboration between experts in atmospheric physics, materials science, planetary geology, astrobiology, theoretical physics, computational modeling, observational astronomy, and advanced engineering. The research methodology itself represents a revolutionary approach to understanding distant worlds, combining cutting-edge theoretical physics with precision observational astronomy and sophisticated laboratory experiments that recreate alien environmental conditions here on Earth. Scientists are literally bringing the universe into Earth-based laboratories, recreating the extreme conditions found in these distant worlds to understand what we're observing through our most advanced telescopes. This interdisciplinary collaboration is producing insights and discoveries that no single scientific discipline could achieve working in isolation, representing a new model for how humanity approaches the biggest questions about our universe and our place within it. The statistical implications of this research become truly staggering when we consider the immense scale of the universe and the numbers involved in galactic planetary populations. If sub-Neptunes represent 30 to 50% of all exoplanet, and our galaxy contains an estimated 100 billion stars with potentially trillions of planets, we're talking about hundreds of billions of these water-rich worlds that could collectively inform our search for life and our understanding of planetary formation processes. Each sub-Neptune we study provides crucial data points for understanding planetary formation, atmospheric evolution, and water distribution on a galactic scale. We're not just studying individual worlds in isolation. We're developing a statistical and theoretical understanding of how planets form and evolve throughout cosmic history, providing insights into the conditions that might lead to life across vast scales of space and time that dwarf human comprehension. This research is helping us understand our galaxy as a vast planetary laboratory where different types of worlds form under varying conditions, creating a cosmic diversity of environments that could potentially support different forms of life or different stages of biological evolution. Beyond the immediate scientific significance, this research challenges our most fundamental assumptions about planetary diversity, the conditions that might support life, and humanity's place in the cosmic order. It suggests that the universe operates according to physical principles that produce outcomes far more varied, complex, and creative than our Earth-centered perspective initially assumed or could have predicted. This has profound implications for how we think about our planet's uniqueness, our solar system's formation, history, and the potential for finding life elsewhere in the universe. If the most common planets in the galaxy are so fundamentally different from Earth and completely absent from our solar system, it forces us to radically expand our imagination about what constitutes a potentially habitable world and what incredible forms life might take in environments we're only beginning to understand. The research suggests that Earth and our entire solar system might be far more unusual and rare than we previously thought, existing as a cosmic anomaly that lacks the most common planetary types found throughout the galaxy. This could mean that Earth-like conditions and the specific sequence of events that led to life on our planet are much rarer than we hoped. Or it could mean that life is far more adaptable, diverse, and creative than we've dared to imagine. Sub-Neptunes may not directly harbor life themselves in forms we would immediately recognize, but they're proving to be invaluable teachers and guides in our species' quest to understand how life arises, evolves, and survives in the universe. These mysterious worlds are revealing that the cosmos is far stranger, more wonderful, more complex, and more creative than we ever imagined, even in our boldest scientific fantasies. From supercritical water behaving like liquid gas to superionic ice that conducts electricity like metal, from thick vapor atmospheres extending thousands of kilometers into space to complex internal dynamics spanning millions of years of planetary evolution, Sub-Neptunes are dramatically expanding our understanding of what's possible in planetary science and atmospheric physics. They're serving as cosmic laboratories, helping us decode the fundamental conditions that could lead to life, providing the theoretical framework, observational techniques, and conceptual foundation for the next phase of our search for extraterrestrial intelligence and our understanding of biology's place in the universe. The universe continues to surprise us with its infinite creativity in generating diverse planetary conditions, exotic physical environments, and complex evolutionary pathways, and every new discovery brings our species closer to answering the fundamental question that has driven human curiosity since we first looked up at the stars: are we alone in this vast cosmic ocean? Mysterious and full of incredible surprises waiting to be discovered, and we're living during the most exciting and revolutionary time in the entire history of astronomy, space exploration, and our species' quest to understand our cosmic home. If you're as fascinated by these mind-blowing cosmic revelations as I am, make sure to hit that like button. It helps the YouTube algorithm share these incredible discoveries with more curious minds like yours who are passionate about understanding our place in the universe and the search for life beyond Earth. Don't forget to subscribe to BrightBoundX and ring that notification bell so you never miss our latest explorations into the brightest frontiers of science, space exploration, cutting-edge research, and the most amazing discoveries. Share this video with anyone being made by scientists around the world. Anyone who's ever wondered about life beyond Earth, alien worlds, the incredible diversity of planets in our galaxy, or the revolutionary discoveries being made by modern astronomy, together, we're all part of humanity's greatest adventure of discovery and our species' journey to understand the cosmos. What do you think about these mysterious sub-Neptune worlds and their potential role in helping us find alien life? Could they really be the key to understanding planetary formation and habitability throughout the galaxy? Do you think Earth's uniqueness in lacking these common planets makes us more special and rare, or does it suggest that life might be more diverse, adaptable, and widespread than we've ever imagined? Drop your thoughts, questions, and theories in the comments below. I read every single one, and absolutely love discussing these cosmic mysteries with our amazing community of space enthusiasts, science lovers, and fellow cosmic explorers. Until next time, keep looking up at the stars, keep questioning everything about our universe, and keep exploring the infinite wonders and mysteries of our cosmic home. This is BrightBoundX, and we'll see you in the next video, where we'll continue pushing the boundaries of human knowledge, cosmic understanding, and our never-ending quest to decode the secrets of the universe. Remember, the universe is under no obligation to make sense to us, but that's exactly what makes it so incredibly exciting, mysterious, and rewarding to explore through science, observation, and human curiosity. Every discovery opens new questions, every answer leads to deeper mysteries, and every observation brings us closer to understanding our cosmic home and our place within the grand story of the universe. Thanks for joining me on this incredible journey to the edge of human knowledge and beyond, into the infinite frontier of space.